Hi, my name is Devin Harsh, and I'll be presenting my poster titled A Common Mechanism Explains Choice, Reaction Time, and Confidence in a Multisensory Heading Discrimination Task. This is based on work I did as an undergrad at Johns Hopkins in the lab of Dr. Chris Fetsch with the help of Dr. Stephen Jerjian. We're interested in how the brain uses perceptual information to make decisions. Humans do this effortlessly, but the computations that underlie perceptual decisions are complex and not entirely understood. Sensory information is inherently noisy or ambiguous, and it arises from multiple sources. And the brain must take the uncertainty of the evidence into consideration when making decisions or assigning degrees of confidence. For this project, we're concerned with decisions regarding self-motion direction, which requires the dynamic integration of vestibular signals from the acceleration of the head through space and optic flow signals arising from the movement of the world across the retina. Using a motion platform and 3D visual display, pictured at the top right, we've adapted a well-established task in which human and monkey subjects report their perceived direction of heading in response to passive self-motion. Subjects were placed inside the motion platform in front of the visual display and presented with interleaved self-motion stimuli, consisting of platform motion, a moving cloud of dots to produce global optic flow signals, or a combination of both. The reliability of the visual self-motion cue was dependent on the proportion of coherently moving dots. Subjects were instructed to make a saccade to one of two targets to indicate their decision about the perceived heading direction relative to straight ahead. And after initial training, subjects are allowed to make their choices as soon as they were ready, provided as a measure of their reaction time. For confidence reports, human subjects made the saccade to a color gradient bar, where the different regions represent a continuous estimate of confidence. Monkeys were trained to first make a saccade indicating their choice, followed by a subsequent saccade up or down as a post-decision wager, which is a proxy for confidence. The task sequence is shown here. So here are the basic patterns of behavior that we see. To start with, I'm only showing the vestibular condition. The first plot shows the choice data. We plot the heading angle relative to straight ahead on the x-axis, with rightward angles being positive and leftward negative. The second plot is the monkey's confidence, or his proportion of high bets, as a function of heading. For larger heading directions, the monkey is, on average, more confident. For heading angles closer to 0, the monkey is less confident. And this shows the link between stimulus difficulty and subjective certainty. We see the inverse in the third plot for reaction time. RTs are fastest for large heading angles and slower for more difficult choices. Now here is the full data set with all the modalities, along with the human data so that you can compare. The post-decision wager task, reward size, and penalty timeouts were adjusted to encourage the monkey to wager in accordance with the prediction of his accuracy, and indeed his accuracy on high bet trials was greater than on low bet trials. Interleaved across the session are trials in which the cues are placed into conflict to measure how the weights change when one cue dominates the monkey's report. This cue conflict manipulation has been used extensively to test for statistically optimal or Bayesian cue combination, and here we apply it for the first time to simultaneously measure RT and confidence reports. The results show a shift in the psychometric curves, indicating a dynamic reweighting of evidence based on the reliability of the cues. Note that a delta of +3 indicates visual to the right and vice versa for -3. Hence, at low coherence, the delta -3 curve shown in blue is shifted to the left, meaning a rightward bias, because the rightward pointing vestibular cue is given a higher weight. With the coherence of 0.8, we see nearly equal cue weighting, as indicated by the overlap of the curves and as predicted by the closer psychophysical thresholds in the single cue conditions. The shifts in confidence and RT also reflect this dynamic weighting, suggesting a common mechanism by which uncertainty impacts all three. And again, here's the human data so you can compare. We modeled the decision process as race between two accumulators. Noisy samples, visual and vestibular evidence are combined in an optimal weighted fashion according to the relative reliability. Evidence samples favoring each of the alternatives, right versus left, are accumulated separately until one reaches a bound, triggering a decision in favor of the corresponding direction. The reaction time is determined by the time the bound is reached, plus an additional non-decision time reflecting sensory and motor delays, which is specific for each stimulus modality. This is shown here on the left. The state of the losing accumulator maps directly onto the log odds of being correct, shown here on the right. And finally, the model predicts that confidence will vary as a function of deliberation time, even for a fixed level of evidence. And as we see in our data here in the top right, for a given stimulus strength, confidence is inversely related to reaction time. We fit the model to our data via maximum likelihood methods, and here are the fits. Note that we used only the non-conflict conditions to fit the model, then used the fitted parameters to predict the reliability-dependent shifts during cue conflict. For the non-conflict conditions, the model does well in capturing most aspects of the data. An optimal cue weighting scheme does not entirely predict cue conflict data, as it underestimates the true size of the shifts. We have some ideas about why this might be, and it relates to post-decision processing of evidence that occurs before the wager is made, or perhaps suboptimal weighting. And I'd be happy to elaborate on this in the discussion if there are any questions. I'll note that this model is still a work in progress, and we have yet to do any formal comparison against alternative models. Joint fitting of choice, confidence, and reaction time may result in some compromise of the parameter fits, which then fails to account for post-choice commitment in the current model. So to conclude, we established a rigorous psychophysical platform to study multisensory decisions with reaction time and confidence. We found that Q conflict manipulation shows commensurate reliability-based weighting in choice, RT, and confidence, supporting the idea of a common mechanism for all three measures. And in the future, we'll be doing a model comparison and neural recording. Thanks.